Okay, once again, here I'm running at 61 volts from the topward power supply down there, and we're indicating a current of 33 or rather 330 to 340 milliamps, right? Average current. And there's the Steve Lear board and the 4 Q2s, and over here is the digital scope display, right? With we're running with no Q1 on time, just oscillations. And here where it says mean average 0 R25 minus 81, 80, 78. Okay, let's just call it 80 millivolts there. Okay, and it's a minus because the trace is actually inverted because of the way the current sense works on this board. But let's say we're indicating an average, a mean average there, mean average of about 80 millivolts. Okay, so now let's go to the calculator. Alright, and what did we have? We have 80 millivolts divided by the current sense resistor, which is 0.25 ohms, and that gives us 320 milliamps. Against 330 milliamps, 340 milliamps. Okay, so I have an error of what? .320 to 340, so 20 milliamps error out of 300 milliamps. No, it was 10 milliamps error. 10 to 15 milliamps error out of 300 milliamps. So that's not bad. 10% would be 30 milliamps. So what if I used 81 milliamps there? Let's see. Oops, sorry about the focus. Oh, 81 divided by 0.25 equals 324. 33034. So that's 16 out of 32, 320, that's 5%. 5% error. Consistently. Okay, thanks for watching. Alright, now notice this. We've got the oscillations going, running strong. We have the, oops, sorry about that. We have the mean average 0R25 there of 77, 78, 79, 80, 81. So between 77 and 81 millivolts there, and that's minus because of the inverted trace, right? Okay, so now what I'm going to do is I'm going to put the snubber circuit on the board. And that shows us what we're getting, some Q2 elevations with a little bit of oscillation there with the snubber on. Now take a look at that same mean average now. 77, 78, 79, 78, 81, 80. So it's within a millivolt or two, within a millivolt really, of what it was before. There's been essentially no change in the mean average computed by the scope from the big oscillation signal to this oscillation here, where you can see a little bit of elevation in the Q2 current. Now, Same thing with the digital multimeter. Here's the jumper. Watch the meter. We're not oscillating now, and now we are oscillating. Wait a minute, sorry. We are oscillating now, 33, 34. Now the jumper is in place, 33. No big oscillations. So the point is that whether or not I'm using the snubber and seeing those big oscillations on the screen like that, or like that, the average current read by the digital multimeter and also by the scope doesn't change, or changes only by a tiny insignificant amount between those two conditions. Okay. Now right now I'm conducting a 60 volt trial with oscillations, so I'm going to leave it in that state, and we'll see how we go. What does it say? 40 over ambient. Alright, the experiment is over. We've done all 60 trials. I've reduced the input power from the main power supply, and looky here, this is still current flowing in the system. Where is that coming from? Well, you'll notice that it's at the same level as before. We even have the same, approximately the same average there, 74 to 78 millivolts. Even the same current indicated there. Well, that's the function generator doing that. That is the function generator, and I'll prove it to you by turning down the amplitude of the function generator. And killing the offset, and there you go. There's the function generator's contribution. So almost all of the power that we were seeing just now in that experiment appears to have been coming from the function generator. Thank you for watching.